Welcome to Unit 2 of AP Calculus AB, Differentiation, in. Unit 1, we built the language of limits. Now we use that language to build one of the most powerful tools in mathematics, the derivative. By the end of this unit, you will know what a derivative is, how to compute it using every major rule, and how to use it to analyze functions. Let's begin. The derivative measures the instantaneous rate of change of a function, not the average change over an interval, the exact rate of change at one single point. Geometrically, this means the slope of the tangent line to the curve at that point. Every time you see a speedometer reading, not your average speed for the trip, but your speed right now. That is a derivative in action. Before we get to instantaneous change, let us review average, rate of change. The average rate of change of f from a to b is f of b minus f of a, all divided by b minus a. Geometrically, this is the slope of the second line. V, straight line connecting the 2 points on the curve. It tells us how fast f changed on average over that interval. The derivative takes this idea and asks, what happens as the interval shrinks to 0? Here is the key geometric idea. Draw a curve and pick A. Point on it. Now pick a second point nearby. The line through both points is the second line, and its slope is the average rate of change. Now watch what happens as we slide the second point closer and closer to the first. The second line rotates, and in the limit it becomes the tangent line, the line that just barely touches the curve at a single point. The slope of that tangent line is the derivative. Here's the formal definition. The derivative of f at x is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. This fraction is the slope of the second line from x to x plus h. As h shrinks to 0, the second point merges with the first, and the second becomes the tangent. The limit of those slopes is the instantaneous slope, the derivative. This definition is the foundation of everything in Unit 2. There are several ways to write the derivative, and you will see all of them on the AP exam. F prime of x is the most common, called prime notation. dy over dx is Leibniz notation. d over dx applied to f of x is operator notation. And y dot is Newton's notation, used mostly in physics. They all mean the same thing. Know them all. A function is differentiable at x equals a if the derivative exists there. Here's the critical theorem if f is differentiable at a, then f must be continuous at a. Differentiability implies continuity. The converse is false. A function can be continuous at a point but not differentiable. There. The classic example is the absolute value function. At x equals 0, continuous, but with a sharp corner, where the derivative does not exist. There are 3 situations where a derivative fails to exist. First, a corner or cusp. At a sharp point, the left and right. Slopes are different, so the limit does not exist. Second, a vertical tangent. If the slope approaches infinity, the derivative is undefined. Third, a discontinuity. If the function has a hole, jump, or asymptote at a point, it cannot be differentiable there. Whenever you find a point of non-differentiability on the AP exam, check which of these 3 cases applies. Now we build our toolkit of differentiation rules. The most fundamental is the power rule. The derivative of x to the n is n times x to the n minus 1. You bring the exponent down as a coefficient, then reduce the exponent by 1. This works for any real number n, positive, negative, fractional. It does not matter. Learn this rule cold. It is the basis for differentiating every polynomial. Let us practice the power rule. The derivative of x to the 5th is 5x to the 4th. The derivative of x cubed is 3x squared. The derivative of the square root of x, which is x to the 1/2, is 1/2 times x to the negative 1/2, which equals 1 over 2 root x. The derivative of 1 over x squared is negative 2 over x cubed. And the derivative of any constant is 0. Every one of these comes directly from the power rule. 2 simple but important rules. The constant rule, the Derivative of any constant is 0. A horizontal line never changes, so its rate of change is always 0. The constant. Multiple rule. If you have a constant multiplied by a function, pull the constant out and differentiate the function. The derivative of c times f of x equals c times f prime of x. These two rules work together constantly when differentiating polynomials. The sum and difference rule. The derivative of a sum is the sum of the derivatives. You can differentiate each term separately. This is what makes polynomials so easy. Just apply the power rule term by term. For example, the derivative of 4x cubed minus 7x squared plus 2x minus 5 is 12x squared minus 14x plus 2. 3 applications of the power rule, the constant multiple rule, and the constant rule, and you are done. When you multiply two functions together and differentiate, you cannot just multiply the derivatives. You need the product rule. The derivative of f times g equals f prime times g plus f times g prime. Memory phrase, first times. Derivative of second plus second times derivative of first. For example, the derivative of x squared times sine x equals 2x sine x plus x squared cosine x. The first term comes from differentiating x squared while keeping sine x, and the second from keeping x squared while differentiating sine x. When dividing two functions, use the quotient rule. The derivative of f over g equals f prime g minus fg prime all over g squared. Memory phrase, low d high minus high d low over low squared. Note the subtraction. The order matters. For example, the derivative of x squared over x plus 1, low is x plus 1, high is x squared. Low d high, x plus 1 times 2x, minus high d low, x squared times 1, over low squared, x plus 1 squared. Simplify to get x squared plus 2x over x plus 1 squared. Here are the 6 trigonometric derivatives you must memorize. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Note the negative sign. The derivative of tangent x is secant squared x. The derivative of cotangent x is negative cosecant squared x. The derivative of secant x is secant x times tangent x. The derivative of cosecant x is negative cosecant x times cotangent x. Notice, the cofunctions all pick up a negative sign. These 6 are non-negotiable on the AP exam. The chain rule is used when you have a function inside, another function, a composite function. The rule says the derivative of f of g of x equals f prime of g of x times g prime of x. In plain English, take the derivative. Of the outside function, leave the inside alone. Then, multiply by the derivative of the inside. Think of it as peeling an onion. Differentiate the outer layer first, then multiply by the derivative of the inner layer. Let us practice the chain rule. The derivative of sine of 3x, outside is sine, inside is 3x. Derivative of sine is cosine. So cosine of 3x times derivative of 3x, which is 3. Answer, 3 cosine 3x. The derivative of x squared, plus 1 raised to the 5th. Outside is something to the 5th, inside is x squared plus 1. Bring down the 5, keep. The inside, reduce the power, times 2x. Answer, 10x times x squared plus 1 to the 4th. Practice recognizing the outer and inner functions. That is the whole skill. One of the most common AP exam questions. Find the equation of the tangent line to a curve at a given point. The method, differentiate f to get f prime. Evaluate f prime at the given x, that is the slope. Use point slope form, y minus. U1 equals meters times x minus x1. For example, f of x equals 0.4x squared at x equals 2. F prime of x equals 0.8x tfs. F prime of 2 equals 1.6. The point is 2, 1.6. Tangent line, y minus 1.6 equals 1.6 times x minus 2. The normal line is perpendicular to the tangent line at the same point. Since perpendicular lines have slopes that are negative reciprocals of each other, the slope of the normal line is -1 over f prime of a. Everything else is the same as finding the tangent line. Use point slope form, with the normal slope. For example, if f prime of 2 equals 4, the tangent slope is 4 and the normal slope is negative 1/4. You can differentiate a function more than once. The second, derivative is the derivative of the first derivative, written. F double prime of x or d squared y over dx squared. It measures the rate of change of the slope. In physics, if position is x of t, then the first derivative is velocity, the second derivative is acceleration, and the third derivative, called jerk, is the rate of change of acceleration. Let us compute higher-order derivatives. Start with f of x equals 3x to the 4th minus 8x cubed plus 2x. Apply the power rule. F prime of x equals 12x cubed minus 24x squared plus 2. Differentiate again. F double prime equals 36x squared minus 48x. One more time, f triple prime equals 72x minus 48. Notice how each differentiation reduces the degree by 1. So far, we have only differentiated functions where y is, explicitly written in terms of x. But sometimes that is impossible. For example, the equation of a circle x squared plus e squared equals 25. You cannot solve cleanly for y. Implicit differentiation handles this. The idea, differentiate both sides with respect to x whenever you differentiate a term involving y. The chain rule gives you a factor of di over dx. Then collect those terms and solve for di over dx. Let us differentiate x squared plus e squared equals 25, implicitly. Differentiate both sides with respect to x. Left side, 2x plus 2y times dy over dx. The second term gets di over dx because of the chain rule on y. Right side, 0. Now isolate di over dx. 2i times dy over dx equals negative 2x. Divide both sides by 2e. dy over dx equals negative x over y. This gives us the slope of the circle at any point in terms of both x and y. Two more families to differentiate. For exponential functions, the derivative of e to the x is e to the x, the only function that is its own derivative. With the chain rule, the derivative of e to the u is e to the u times u prime. For logarithms, the derivative of natural log of x is 1 over x. With the chain rule, the derivative of natural log of u is u prime over u. For other bases, the derivative of a to the x is a to the x times ln a. The derivative tells us where a function is increasing or decreasing. If f prime of x is greater than 0 on an interval, then f is increasing there. If f prime is less than 0, f is decreasing. If f prime equals 0, the function has a horizontal tangent. It might be at a peak, a valley, or just a flat point. This is the first step in analyzing the shape of any function. A critical point is any x value where f prime of x equals 0, or where f prime of x does not exist, but f itself is defined. Critical points are the only places where a local, maximum or minimum can occur. Finding them is always the first step in optimization problems. Set f prime equal to 0 and solve. Also check any x values where the derivative is undefined. Every critical point is a candidate for an extremum, but you need a test to confirm. The first derivative test tells us whether a critical point is a local max, a local min, or neither. Evaluate the sign of f prime on either side of the critical point. If f prime changes from positive to negative, the function was rising, then fell. You have a local maximum. If f prime changes from negative to positive, the function was falling then, rose. You have a local minimum. If f prime does not change, sign, the critical point is neither. Build a sign chart. Mark the critical points, test one x value in each interval, and read off the signs. The second derivative tells us about concavity. If f double prime is positive, the graph is concave up. The slope is increasing. If f double prime is negative, the graph is concave down. The slope is decreasing. An inflection point is where the concavity changes. Where f double prime changes sign. To find inflection points, set f double prime equal to 0 and check if the sign actually changes on either side. L'Hopital's rule is a technique for evaluating limits that produce indeterminate forms like 0 over 0 or infinity over infinity. The rule says if the limit of f over g produces an indeterminate form, then the limit of f over g equals the limit of f prime over g prime. You differentiate the numerator and denominator separately, not as a quotient, and try again. For example, the limit of sine x over x as x approaches 0 gives 0 over 0. Applying the rule, limit of cosine x over 1 equals 1. Related rates problems involve two or more quantities that both change over time and are connected by an equation. The strategy, draw a diagram and label the quantities. Write an equation that relates them. Differentiate both sides with respect to time t. Every variable gets a d over dt factor. Plug in the known values at the specific instant and solve for the unknown rate. Common setups include expanding circles, falling ladders, filling tanks, and moving shadows. Let us summarize Unit 2. The derivative is the limit of the difference quotient as h approaches 0. The power rule, bring the exponent down and reduce by 1. The constant. Multiple and sum rules let you differentiate polynomials, term by term. The product rule, first times d second plus, second times d first. The quotient rule, low d high d low over low squared. The chain rule, derivative of, outside times derivative of inside. Implicit differentiation, handles equations where y is not isolated. The sixth trig, derivatives, exponential and log derivatives. Critical points, where f prime is 0 or undefined. The first derivative, test for local extrema. Concavity from the second derivative. L'Hopital's rule for indeterminate forms and related rates for changing quantities. That is Unit 2 of AP Calculus AB. You have gone from the limit definition of the derivative all the way through, related rates and concavity analysis. Unit 3 builds directly on this. Composite functions, implicit differentiation at a deeper level, and inverse function derivatives. Subscribe so you do not miss it. See you in Unit 3.